so let's say I insert my first key value pair, and for some, it undergoes some compression function and some hash code function, and it hashes to the 0th bucket. And so let's say K stands for key, V stands for V. We'll call the key goo, and the value is jello. Okay, so then now let's say we insert another item, and the key hashes to bucket 4. We'll call that, so the key ends up being Java, and the value ends up being another string is awesome. This is the value. Okay, now however, let's say we insert another item, and that also hashes to 0. So what happens next is it creates a node of the key value pair and inserts it at the end of the list. And so this ends up being, let's say, hello, and the value is goodbye. These are just all arbitrary placeholder values, but I'm sure you get the idea. What's happening is these things are all chaining together. So you have a chain of elements that are being chained together every single time a collision happens. So as a result, the more times keys hash to the same bucket, in that corresponding bucket, the length of the S list grows longer and longer and longer and longer. And we'll see why that isn't always the best thing and can be avoided if we have a nice even distribution of keys hashing to different buckets, rather than like a bunch of keys hashing to the same bucket. This is how we optimize hash tables, which we'll talk about later next time in the next video. So now that we understand what's going on in this S list, let's talk about the different methods we can utilize with the S list, and let's analyze their runtimes, just like we've done in the past. So the first one is, as I'm sure you've seen before, find. We need to find a specific value. We're given a key, some object, and we're given a key, and we need to determine the value in the hash table. Well, all you have to do is you take the key, get hash code, then 2, compress it, and then 3, get the value by searching through the S list. And you can see why this is sometimes problematic, right? Because if you have an S list with a ton of collisions, you basically have to search through the S list in n time. And so let's just say for some crazy reason you insert n items, and those n items all hash to the same bucket. As a result, in the worst case scenario, you end up searching for a value ends up taking worst case linear time. However, because of amortized analysis, and we're assuming that we do this is like a good this is a good hash table, or a well-designed hash table, then usually these are all going to be this is going to be in a primitive operation, another primitive operation, another primitive operation, meaning find ends up working in constant time. And we'll also discuss a technique called amortized analysis in the future, which allows me to prove why the hash table almost always works in constant time for the find operation, and for the other two, which I'll talk about right now. So the next operation, which I'm also sure you've seen, is the insert operation. We're given a key, and we're given a value. Both are objects. Okay, and we want to insert it. We want to insert this key value pair into the hash table. So same thing as before. Get hash code. To get bucket number by compressing the hash code. And then 3, actually inserting to end of S list. Okay? And that's really it. That's really it for end. And so this ends up being a primitive. 1 is a primitive operation. 2 is a primitive operation, right? And 3 ends up also being a primitive operation. If you want to insert to the end, you have tails going on. Or if you insert it to the beginning. So let's just say we just insert it to the beginning to make life easier. So inserting it to the beginning. So this ends up, you're guaranteed that insert will work in constant time. So the next question is, what about remove? So the remove also works the same way. You have some key. Most of the time they will give you a key. They're just going to give you the key, and you want to go. You want to do literally the same thing. You want to do the same thing as find. So you want to find the key value pair, and then just remove from slist. If it's there. If it's not there, just return null or whatever. So this ends up being a primitive operation, and this also is a primitive operation because you're just changing pointers around, right? So this takes like at best 3 operations. This definitely takes like this ends up taking like 2 or 3 operations as well. So this also remove is guaranteed to always be in constant time. And so that's why remove and insert are always going to be in constant time, and find, if you use a multi-test analysis proof, is mostly always going to be in constant time as well, if the hash table is designed nicely. So that's why the hash table is such an amazing data structure, because it's so blazingly fast. You can find things, remove things, insert things in constant time, and you can augment the hash table with other data structures to do things extremely quickly. So I hope that you enjoyed this discussion of hash tables. We're still not done yet, as we have to discuss hash table optimization and analyzing bad compression functions and analyzing bad hash code methods, as well as amortized analysis. So it's going to be a jam-packed schedule, but hash tables are amazing, and I'm sure you're going to like it. So stay tuned.